So dear students, I am continuing with my last class where I could not answer some of your questions, and there was a lot of problem in organizing those real-time class in Microsoft Teams. So I decided to make a video recording of my teaching and upload in the YouTube platform and share the link with you in our WhatsApp group. So I am continuing with my last class, and I have that was the name, that was the title of my of the class which I am carrying on and started in my last day yesterday. So I named this class as Cardiac Biomechanics from Cell to Circulation. I repeat, Cardiac Biomechanics from cell to circulation. So this is a significant phrase. If you understand this phrase, this combination of these words in real meaning, in real way, then you understood everything about our mechanical performance of heart. So my aim is to make you understand the mechanical performance of heart in general and mechanical performance of ventricle in particular in healthy state, in healthy physiological state, and also in certain disease state. So that is my aim, and with that aim I will continue with my class for another 2 or 3 sessions. So altogether 4 or 5 classes are allotted to make you understand the mechanical performance of heart in general and ventricle in particular. Now, the section which I am discussing now from my last class is mechanical performance of isolated cardiac muscle. So I have started from cell, as I mentioned here, I have started from cell and I will proceed to circulation. So for the time being, I am discussing the mechanical performance of an isolated cardiac muscle. Now, when I was discussing the resting length tension relationship during my last class, some question raised and some of you posted some questions in my WhatsApp group, and I also discussed over telephone of some of you, and I understood there are certain fundamental deficiency of understanding of some of the aspects of muscular function. Although the nerve muscle physiology are being taught, but somehow due to whatever reason, the conception, certain fundamental conception is lagging in you. So I thought that first of all I need to discuss those fundamental conceptions. One of such fundamental conception is what we understand by the basic property of muscle contraction. By muscle contraction, I mean the contraction of striated muscle. What are the striated muscles? Striated muscles are the skeletal muscles and cardiac muscles. Skeletal muscle means those muscles which are attached with the skeleton, the bony skeleton. And when those muscles contract or when those muscles shorten, that will lead to pulling of the skeleton, and when the skeleton is being pulled, there will be displacement, and when there is displacement, some work will be done and there are certain performance will be done due to that contraction. So contraction lead to shortening, shortening lead to pulling of the skeleton, pulling of the skeleton will lead to displacement of some or whole part of our body, and accordingly some work will be done. So this is a kind of contraction and its consequence which we occasionally observe in case of skeletal muscle system. But there are situations when a skeleton does not move even even as a consequence of a powerful muscular contraction. I repeat, there are situations when a skeleton does not move, or when a part of the skeleton does not move, or more specifically a limb does not move even after a powerful muscular contraction. This also happens. So let me discuss both of them. And what is its implication. Now you must have heard two fundamental types of muscle contraction. One such is known as isotonic and another is isometric. So one such contraction is known as isotonic contraction, and one such contraction is known as isometric contraction. Now today when I was discussing with some of your friends, some of your classmates over telephone, I asked this question that what is isotonic contraction, what is isometric contraction. All of them correctly answered that isotonic contraction is that contraction when skeletal muscle shortens or muscle shortens without change in tension, and isometric contraction means when muscle does not shorten with generation of tension. So all of them unhesitantly could answer the correct answer of these two questions, what is isotonic and what is isometric. And I understand most of you know this definition, that isotonic contraction means there is shortening of muscle without change in intramuscular tension, and isometric means there is no shortening of the muscle, no change in length of the muscle with generation of tension. But when I asked what is the implication, what does it imply, what does it specifically signify in our physiological system, none of them could clearly answer. So I understood there are certain basic point of deficiency of conceptualization of all these things. Now if I ask you, as I cannot interact with you, this is a video recording class, if I ask you, can you give me an illustration or example of isotonic contraction? All of you can answer. So suppose we are moving our hand, moving here and there, so this is isotonic contraction, there is displacement, there is work done. But if I ask you, give me an example of isometric contraction, I am sure, 100% sure, all of you will answer that I will push a wall. A pushing a wall is classically denoted as an isometric contraction. Probably it is there in your high school biology book. But I understand in my experience of several decades of teaching, when it is asked to a student that give me one example of isometric contraction, all of them answer that I will push the wall. And by hearing this answer, every time I get irritated, and every time when I ask the question nowadays, I always tell them, I put a precondition, I put a disclaimer that give me an example of isometric contraction without stating that pushing of a wall. And if I give this precondition, most of the time students could not answer. So there is serious lack in understanding of what is isotonicity and isotonic nature of contraction and what is isometric nature of contraction. So I understand before entering into the intricacies of cardiac muscle contraction, I need to clarify this issue. I need to clear this issue beyond any reasonable doubt so that you can conceptualize what is isometric contraction and what is isotonic contraction. Now let me play the role. So whether a muscle will contract isotonically or isometrically. What is the answer? Whether a muscle will contract isotonically or isometrically. To put this question you need to know one more thing. What is that thing? That is, every muscle, skeletal muscle or cardiac muscle, every muscle, if I for the time being discuss about the skeletal muscles, a skeletal muscle can, a single skeletal muscle or a particular skeletal muscle can contract isometrically as also it can contract isotonically. A muscle, suppose this is biceps brachii, this is biceps brachii, this one, and this is a flexure of the elbow. If the biceps brachii contracts, the elbow is flexed. So this is a flexion of the elbow, biceps brachii. This biceps brachii can contract isotonically and also it can contract isometrically. Biceps brachii muscle can contract isotonically and it can also contract isometrically. When it will contract isotonically and when it will contract isometrically? So that is my question. The explanation is, or the answer is, whether this biceps brachii as a skeletal muscle contract isometrically or isotonically is entirely dependent upon the load, the resistance it assigned to undertake during the contraction. The load it is assigned to overcome during its contraction. The resistance this muscle is expected to surmount during its contraction. That is the factor which will determine whether this biceps brachii will contract isometrically or isotonically. If I explain it in more elaborate way, so what is a load? So when the biceps brachii is contracting, by contraction it is causing flexion of the elbow. By flexion of the, how the flexion of the elbow is taking place? Because biceps brachii tendon is inserted on the forearm bones, say humerus and radius and ulna, etc., forearm bones. So when biceps brachii contract, this skeleton will be pulled and elbow will be flexed. So here these forearm bones, radius, ulna and all the muscles attached with it, along with all the bones of the hand, all the muscles attached with the tendon, the weight of this forearm, whole of this forearm is acting as a load. This load need to be overcome by the powerful contraction of the biceps brachii. Now in addition to that, I can add some extra load. Suppose I am adding some extra load here. I am adding some extra load here. I am adding some extra load here. I am adding some weight here. If I go on adding some extra load here, more and more I add some load, more and more the biceps brachii has to overcome that extra amount of load. So it is the load which will determine whether biceps brachii will contract isometrically or isotonically. Suppose I put a small load along with the existing load of the weight of the forearm, etc. I add a small load and biceps brachii can easily elevate the load. But instead of this small load, if I put 2 bricks, say a 2 kg weight or 3 kg weight or 5 kg weight here, and thereby increasing the total load which the biceps brachii has to overcome, what will happen? It will fail to elevate the load. It cannot elevate the load. Suppose I put 2 bricks, dukhana eat, 2 bricks are put here or 3 bricks are put here, and by powerful contraction I cannot overcome that load. What will happen? The biceps brachii will contract very hard. Very hard. It will try utmost to overcome the load, but it cannot do so. And as it is cannot overcome the load, cannot elevate the load, so the length of the biceps brachii will not be shortened. And as the length of the biceps brachii is not shortened, it cannot pull the skeleton and the elbow will not be flexed. Can you understand this? So it is simply the load which a particular skeletal muscle has to overcome, has to surmount, has to elevate, will determine whether that particular muscle will contract isotonically or isometrically. In case of isometric contraction, the length of the muscle remains same, but in its attempt to elevate the load, or as it is contracting, the intramuscular tissue tension will rise enormously. The intramuscular tissue tension will rise enormously, muscle will become hardened. But in spite of that, the length remains same. So it's an isometric contraction with a high intramuscular tissue tension, but no change in length. Whereas, when it can elevate the load, the change in length is shortened, skeleton is pulled, work is being done, and movement is being performed, and the tension inside the muscle remains same. So it is isotonic, one is isotonic, another is isometric. So if you understand that, then I will proceed to a more objectivized description or explanation of this phenomenon. More objectivized or more graphical, not graphical, more elucidative description or explanation of this thing. So, to understand this isometric contraction and isotonic contraction in a more or further detail, now let us, I told you earlier probably that the way of biological description, the way of description of the physiological phenomena is usually that we take up some example from the physical science, either physics or mathematics, etc. We take certain example, some established model from the physical sciences, pure sciences, and apply that model in biological sciences with reasonable degree of approximation and try to understand the biological phenomena. That is a way, that is a age-old way to understand biological things. So, to understand this muscle contraction, isometric contraction, isotonic contraction, tension generation, and change in length or no change in length, tension generation or no tension generation, change in length or no change in length, all these things is classically explained by a particular form of presentation which I will try to explain now. Now suppose I am drawing a muscle. I am drawing a muscle. So, if I say that I have drawn a muscle, I have drawn a illustrative schematic presentation of a muscle, would you agree with me? Certainly not. What it is apparently looking like? It is like a kind of a circuit diagram. Isn't it? It is looking like a circuit diagram where there are certain resistance and there are certain a kind of a capacitor kind of thing, and there are two ends. And I have written so many things here. So let me explain first. So this is a muscle. This is a muscle. This is the origin end of the muscle and this is the insertion end of the muscle. What is origin end of the muscle? Origin end of the muscle is that end of the muscle which is relatively fixed. And insertion end of the muscle is that end of the muscle which is relatively mobile. So what is origin? Origin end of the muscle is that end of the muscle which is relatively fixed, and insertion end of the muscle is that end of the muscle which is relatively mobile, and it is the insertion end which is attached with that portion of the skeleton or that portion of the load which it is assigned to elevate or overcome or surmount. So this is relatively fixed end, this is relatively mobile end, and this is the end where the load is applied. Where the load is applied. So if we apply a load, so this is the load. This is the load which the muscle is assigned to elevate. This is CC, means contractile component. What is contractile component? Contractile component is the myofilaments, etc., thick filament, thin filament, actin, myosin, tropomyosin, etc. That complex which will lead to sliding filament mechanism and thereby causing contraction, which are being discussed in detail, I understand, in muscle physiology. ACC means series elastic component. Again, ACC means series elastic component, and PEC means parallel elastic component. So in a muscle there is a contractile component, and there are two kind of resistance, two kind of springs. One is kept in series, either in the tendon or in series with the contractile component, and another type of spring or elastic element which is kept in parallel, either a covering of the muscles, etc., having certain elastic property. And it is finally attached with the insertion end, and this is the load which is applied. Now in this situation, when the muscle contracts, what will happen? There is shortening of sarcomere, or actin, myosin, or thick and thin filament will slide within each other and try to move towards center. So it will tend to slide in. Now when the load is trivial, load is small, when the load is trivial, what will happen? They will go inside. The overall length of the sarcomere will be reduced, and that is sufficient to shorten the muscle, shorten the overall length of the muscle. And when the overall length of the muscle is shortened, this load is overcome. So when the load is small, when the load is trivial, or when the load is surmountable, by simple reduction in the sarcomere length, the overall muscle length will be shortened, reduced, and it will pull or elevate the load. And that is the story of isotonic contraction. Now, instead of this small trivial load, if we apply a very big load here, 2 bricks or 2 volumes of Gray's Anatomy. Have you ever seen Gray's Anatomy? So, if we put 2 volumes of Gray's Anatomy or 2 bricks, something like that, what will happen? There will be enormous load, And in that situation, both the origin end and insertion end will behave as a fixed end. Both ends will behave as a fixed end. This is a relatively fixed end already, and this becomes fixed end due to application of a heavy load. So both become fixed end. And in that situation, what will happen? When the muscle will tend to contract, when the muscle will tend to contract, it cannot shorten because both ends are fixed end. It cannot shorten, as a result of which the series elastic component, mainly the series elastic component, and also to some extent parallel elastic component, they are stretched. They are stretched, and as they are stretched, that will lead to genesis of tension, genesis of intramuscular tissue tension. So what will happen when the load is high? The muscle length will remain unaltered. Muscle length will remain unaltered. It is not shortened, but pulling of this ACC, series elastic component, mainly to some extent PEC, leading to generation of intramuscular tissue tension. So tension will increase. So when I have applied a load here, it is trying to elevate, it cannot do so, but the biceps brachii becomes taut, hardened, due to development of enormous amount of intramuscular tissue tension, but the length remains unaltered. So this is, if you understand this diagram, that is very good. Because then you can understand that how the different components, that is contractile component and various elastic component, are interacting with each other, and how the load remains the primary determinant, primary and fundamental determinant of deciding whether the muscle will contract isotonically or isometrically. If the load is heavy, muscle contraction is isometric. If the load is not that heavy, trivial, the muscle contraction will be isotonic. So this is something about the basic understanding of what is isotonic and isometric. Now this conception of isometric and isotonic, now, so one thing I can summarize, that isometric contraction means no change in length, development of intramuscular tension. Isotonic contraction, change in length, intramuscular tension remains same. And that is my explanation towards that. So with this conception in the backdrop of our mind, if we now try to understand my earlier diagram, which was taught in my last class. What I taught there, I explained, I tried to describe an experiment. Where I attached a strip of muscle, attached a strip of muscle with a sliding bar, and by moving this bar above and below, I can change the length of this muscle strip. I explained that. So I can move this bar above and below, and each time I am moving the bar say down, the length of the muscle strip will increase. And every time I record the resting tension by this tension transducer. So this is a tension transducer. This is a tension transducer. So with the help of this tension transducer, every time I record the resting tension of the muscle, and after recording the resting tension of the muscle, I stimulate the muscle by an electrical impulse. I stimulate the muscle by an electrical impulse and I record the contractile tension of the muscle. So that is my experimental protocol, that I am changing the resting length of this muscle strip, and every time I am measuring the resting tension and also by application of stimulus recording the contractile tension. That is the experiment, and then I plot everything. Then I plot everything, and what I plotted? I plotted this thing. So this is the L0, this is tension. So in x-axis, the independent variable is resting length and dependent variable is tension. So x-axis L0, y-axis T, and we first draw the resting tension curve. We first draw the resting tension curve or passive tension curve, PT or RT. Then we draw the total tension curve or contractile tension curve, TT. And by subtracting them at each level, at each stage of length change, by subtracting them, we obtain the active tension curve in red. So this is active tension curve. So these are the three curves. These are the three curves which I elaborately described in my last class. Elaborately described. So now you understand that in case why I use tension here, because in what I was executing was an isometric contraction. So I am keeping the two ends of the muscle fixed, measuring the resting tension, applying stimulus, measuring the contractile tension. Again I change the length of the muscle, measuring the resting tension, applying stimulus, measuring the contractile tension. Again I am changing the length of the muscle. So when the muscle is being stimulated, both ends are fixed. The length is not changed. Only thing is developing is the tension. So I have wrote tension. So what I am measuring is the tension, intramuscular tension. So it is tension and it is L0 or resting length, and this is my picture. And how this picture is generated, how these graphs are generated, in my last class I described elaborately. Now one question raised by you, and many of you asked the same question, which I failed to probably, although I explained it, but somehow you could not understand that. Now when I discussed that, I also discussed about the differential behavior of this resting length tension relationship curve between skeletal muscle and cardiac muscle. The differential behavior of this resting length tension relationship curve between skeletal muscle and cardiac muscle. Truly speaking, the picture I have drawn here is a picture of a skeletal muscle. Picture I have drawn here is the picture of a skeletal muscle. If this would have been a cardiac muscle, the picture will be a little different, where the passive tension curve will raise much earlier. Passive tension curve will be raised much earlier, even before that. So this is passive tension curve in case of cardiac muscle, and this is passive tension curve in case of skeletal muscle. So what I told you, that passive tension curve of the skeletal muscle and cardiac muscle, they differ. Passive tension curve of the cardiac muscle is steeper, raising much earlier, whereas in passive tension curve of skeletal muscle are raising much flatter. It is much shagger and it is raising much later. And what is the implication? The implication is that as the passive tension curve of the cardiac muscle is raising earlier, it is making the operation of active tension curve within the ascending limb. Usually the length tension relationship curve in resting state, in physiological state, is ordinarily operated within the ascending limb. I made this statement, I tried to explain it, but somehow you could not understand. So I am again explaining the issue, because a lot of you asked the same question. Now try to understand what is passive tension. Passive tension means the tension developed or tension present in the muscle when it is at rest. Tension present in the muscle when it is at rest. Now, when it is at rest, that means every time I am changing the length of the muscle and keeping it at rest. Not rest, rather it should be said passive. I wrote in passive tension. So, when it is passive, not really rest, although we sometimes lightly call it rest, but it is not really rest, it is passive. Passive means it is not stimulated by an electrical stimulus. So every time I am measuring the tension of the muscle when it is passive, and next occasion I am changing the length of the muscle, again measuring the tension of that passive muscle strip. So what does it indicate? It indicates the elastic tension developed as a result of stretching within the muscle when it is at rest. Suppose we have got two kinds of spring. One is a very strong spring which is difficult to stretch, hard to stretch, very stiff type of spring which is difficult to stretch, difficult to lengthen. And then another kind of spring may be there which can be easily lengthened, which can be easily stretchable. Try to understand that two type of spring. So in one kind of spring which is very stiff, if you stretch them more and more, you will experience more and more resistance to stretching. So a very stiff type of spring, very stiff type of spring, if you try to stretch it, initially you can do that, but as you are stretching more and more, you will experience too much resistance to stretch it further. Whereas in case of a light spring, you can easily stretch. That also offers some amount of resistance after some time. So in case of skeletal muscle, the elasticity is such you can stretch initially easily and later you will feel the resistance. Whereas in case of cardiac muscle, it will offer a significant resistance, a remarkable amount of resistance even from the very beginning, or little after very beginning, little after sometimes after the beginning. And as we are stretching more and more, as we are increasing the resting length of that particular muscle fiber more and more, the resting tension or this passive tension is increasing high and high. And as the passive tension is increasing more and more, it will be very difficult to stretch it more and more. If the passive tension with increasing length is increasing more and more, progressive increase in length, it will lead to rise in the passive tension. It will also prevent further stretching. So, as it is rising pretty earlier, this rise in passive tension will prevent further stretching of the cardiac muscle fiber. So, somewhere here the tension is quite high. Somewhere here the tension is quite high. So much so you cannot stretch it further, as a result of which in ordinary physiological normal situation the active tension curve will remain within the ascending limb. If we tend to stretch from here to here to here to here, the passive tension curve is rising so high, it will prevent further stretching. So this early rise of this passive tension curve is acting as a defense, as a defensive valve, defense against overstretching of the cardiac muscle fiber. So cardiac muscle fiber cannot be overstretched. Why? If I repeat that, if you try to overstretch, or if by any mechanism this cardiac muscle fiber is tend to overstretch, due to early development of enormous amount of passive tension, will prevent that kind of further stretching like that of the will prevent. So if you tend to stretch it, a tough kind of spring, a steep kind of spring, so-called spring of this cardiac muscle fiber will prevent or will resist further stretching, and thereby keeping the active tension curve within the ascending limb. So I don't know whether you can understand it or not. If you even cannot understand it, just hold on. Try to remember this much. We shall have other occasions to explain it to you further. Now, so having been said that, let me simplify the whole issue. Instead of such a complex diagram. If I summarize the whole thing, what I have taught till now, if I summarize the whole thing as I have taught till now in simplified diagram, let us see whether you agree with me or not. So if I draw a simple diagram, so this is L0, this is tension, this is passive tension curve, and this is active tension curve. So this is active tension curve, and this is passive tension curve. So this is active tension curve, this is passive tension curve. I have intentionally drawn the active tension curve only the ascending limb, because it is operating up to the ascending limb. Because up to here the passive tension is too much, substantially high, to prevent further stretching. So it is ordinarily operating within the ascending limb of the active tension curve. Now, so if this is the final summary of the length tension relationship curve of isolated cardiac muscle fiber, if this is the summary of the whole issue, what I have described for last 40 minutes, then try to understand the implication of this. So if we try to extrapolate it, or apply it in the whole heart, I told you in my initiation of this class that we shall try to understand the cardiac biomechanics from cell to circulation. So I was discussing at the cell level. Now let us try to understand what is the implication in the whole heart. So our whole heart is also behaving as a single unit. Our heart is a syncytium in nature. I have described in my last class. Our heart is a syncytium in nature. So it is also behaving like this. It is also being passively stretched. If we think about the ventricle, it is also being passively stretched like this. and it is also being actively behaving like this. So this is the passive stretch pattern of the ventricle, and this is the active behavioral pattern or active state pattern of the ventricle. And if we just rewrite it, instead of L0, we can write like that: end diastolic ventricular volume. That means the amount of blood present in the ventricle, each ventricle, amount of the blood present in a single ventricle at the end of diastole. That means at the end of the ventricular filling. At the end of the ventricular filling, the amount of blood present in the ventricle, that will determine the resting length of the cardiac muscle fiber. That will determine the resting length of the cardiac muscle fiber, the amount of blood present. So, as the ventricle is being filled gradually from vena cava, and at the end of the diastole, the amount of blood present there, that will act as a stretching factor. In our experiment, I have shown you by a sliding bar pulling the length of the muscle fiber. Here, the accumulated amount, cumulative amount of the accumulated blood at the end of the ventricle will determine the degree of stretching of the muscle fiber. So instead of L0, we can write like that: end diastolic ventricular volume. Every time end diastolic ventricular volume is changing, and the curve will behave accordingly. And what about tension? This tension which is generated there will lead to development of pressure in the ventricle. Tension which is generated in the ventricular muscle will lead to development of intraventricular pressure, and that intraventricular pressure will act as a factor to eject the blood, eject that amount of blood from the ventricle, So this tension can be suitably equilibrated with the amount of blood which is coming out, that is stroke volume. With each bit, the stroke volume. So we can equilibrate. This diagram can be equilibrated in such a fashion with little bit of transformation factor, and specific equation also can be stated. So in L0 is extrapolated as end diastolic ventricular volume, and tension is finally expressed as stroke volume, amount of blood which is ejected from each ventricle per beat, and it will behave like that. So then that will indicate the pattern of ventricular filling, because filling is taking place when ventricle is in passive state. When the ventricular filling is taking place, when the ventricle is in a state of passive state, resting state, unstimulated state. And this is the pattern of contraction when the ventricle gets stimulated by the incoming stimulus from the atrial level, and it will contract as a whole because it is a syncytial structure. It will behave like that. So in other words, we can call it is the pattern of ventricular filling with changing end diastolic ventricular volume. Suppose if there is a particular amount of end diastolic ventricular volume, that will lead to a particular kind of filling. If the end diastolic ventricular volume is increased, that will lead to further filling and further increase in tension. End diastolic ventricular volume changes. Suppose you are lying in a resting state, we have got a particular ventricular volume, then I am exercising, as I am doing some activity, my ventricular volume is increasing. Suppose I am running, walking briskly, walking up the stairs, my ventricular volume will increase. So as the end diastolic ventricular volume will increase, my filling will gradually increase, and filling tension will also increase. So this will follow a filling curve, and that is a performance curve. Active state, I have told you the active state. So this is the performance curve which will determine the stroke volume. So this is the filling curve and this is the performance curve. Or in other words, so I can write like that. Instead of AT, I can write as a performance, and instead of PT, I can write as a feeling. So this is a feeling curve and this is the performance curve. So this is a characterization of ventricular feeling or ventricular relaxation characteristics. And this is the performance, this is the representation of ventricular activity or ventricular performance. Or if I am allowed to go further and further complicate the issue for you, I can, instead of feeling, I can write as a diastole. I can write as a diastole, and instead of performance, I can write as a systole. So this is a systolic function curve and this is the diastolic function curve. So specifically, so these are the ventricular performance curve. One is during resting state or feeling state or diastolic state. Another is during performance state, active state or systolic state. Systole means performance, ventricular contraction. Diastolic means resting or ventricular relaxation. So this is the relaxation curve or diastolic curve. This is the performance curve or systolic curve. And so this is the, and in between, this is the area where actually ventricle works. So this is the activity zone. This is the activity zone. Ordinarily, it remains active in a small zone. But rest part is a reserve zone which ventricle can extend with increasing level of activity. As I am increasing my activity from resting state to walking, from walking to brisk walking, from brisk walking to jogging, from jogging to running, from slow running to fast running, as I am increasing my range of activities, the ventricular performance is increasing from here to here, to here, to here. So these are the reserve region. Suppose resting state is this much and these are the reserve region during which our ventricle can perform. So this is the resting pattern, this is the active pattern, and in between this zone, this area between the curves, area between these two curves are indicating the ventricular performance zone in resting state and in various levels of activity. So if you understand this much, I will stop here. If you understand this much, that will give us a lot of advantage in understanding certain future issues like more intricate issues of ventricular performance and its changes in various disorder like heart failure. So when we shall discuss heart failure, we shall again bring about all these issues and try to understand what will happen to our feeling pattern, what will happen to our performance pattern in various kinds of disorder. Thank you. So if you have any question, you just post it in our WhatsApp group. I will try to organize an interactive session and try to answer all of them. Thank you.